A bullet leaves the barrel of a rifle, traveling faster than sound itself, carrying enough force to punch through solid steel. And yet, somewhere on the other side of a sheet of glass, a person can stand completely still and watch it stop just inches from their face. That's not science fiction. That's chemistry, physics, and one of the most fascinating manufacturing processes on Earth. So how do you turn something as fragile as glass into a shield strong enough to defeat a rifle round? Let's find out. It all starts with raw glass, but not the kind you'd find in a window. Manufacturers begin with multiple sheets of high-quality float glass, each one inspected for microscopic flaws, because even a tiny bubble or scratch can become a weak point under extreme pressure. These sheets are cut into precise dimensions using automated cutting tables guided by computer-controlled blades, ensuring every panel is perfectly uniform before it moves further down the line. But glass alone, no matter how thick, would shatter instantly under rifle fire. So here's where things get really interesting. The real strength doesn't come from the glass at all. It comes from what's sandwiched between the layers. Between each pane of glass, technicians place thin sheets of a tough polymer interlayer, most commonly polyvinyl butyrol, or, in advanced applications, polycarbonate. This material acts like a shock absorber, flexible enough to stretch and catch fragments, yet strong enough to hold the glass together even after it cracks. Think of it like the mesh inside a car's windshield, just far more advanced and layered many times over. Once the glass and polymer sheets are stacked in alternating layers, sometimes 7, 8, or more, depending on the required protection level, they're carefully aligned by workers wearing cleanroom gloves. Even a single speck of dust trapped between layers could create a failure point later. So this stage demands incredible precision. This is the step most people never get to see. The stacked layers are loaded into a massive autoclave, a giant pressurized oven that looks more like something from a submarine than a glass factory. Inside, the temperature rises to around 140 degrees Celsius, while pressure builds to roughly 150 pounds per square inch. Under this intense heat and force, the polymer melts just enough to fuse permanently with the glass, bonding every layer into a single, solid slab with zero air pockets. The process can take several hours, and workers monitor it constantly, because rushing this stage would compromise the entire panel. What happens next might surprise you. Once removed from the autoclave, the glass isn't done. It has to cool slowly and evenly. Rapid cooling could introduce stress fractures invisible to the naked eye, but catastrophic under ballistic impact. Now comes one of the most nerve-wracking parts of the entire process: testing. Bulletproof glass isn't just manufactured, it's proven. Sample panels from the production batch are taken to a testing range, where they're mounted exactly like real installations and fired upon using standardized ammunition, following strict national or international ballistic resistance standards. High-speed cameras capture the impact at thousands of frames per second, revealing the exact moment the bullet flattens and stops within the layered structure. The real magic happens here. As the bullet strikes, the first layer of glass shatters instantly, absorbing and dispersing the initial kinetic energy. But instead of flying apart, the shattered fragments stay locked in place by the polymer layer beneath. Each subsequent layer slows the bullet further, converting its deadly momentum into heat and pressure spread harmlessly across a wider surface area. By the time the round reaches the final layer, it has lost virtually all of its force, sometimes stopping just millimeters from breaking through completely. If a panel fails this test, the entire batch is scrutinized, and adjustments are made to layer thickness, polymer composition, or lamination pressure. Nothing reaches the market without passing rigorous, repeated testing. Once a batch is certified, the approved panels move to precision cutting and edge finishing stations, where computer-guided saws trim them to exact architectural or automotive specifications. Edges are polished smooth to prevent stress points, and in many cases, the glass is framed with reinforced materials to further stabilize it during installation. Quality control doesn't stop there. Each finished panel is visually inspected under bright lighting to check for optical clarity, since bulletproof glass still needs to be as transparent as ordinary glass for practical use in banks, embassies, armored vehicles, and government buildings. Thickness is measured at multiple points to ensure absolute consistency, because even a slight variation could weaken the panel's overall performance. Finally, the panels are carefully packaged using protective padding and rigid crating to prevent damage during transport, since, ironically, the glass that can stop a bullet can still be vulnerable to cracking from a hard impact during shipping. From there, these panels are distributed to security firms, automotive manufacturers, and government contractors around the world, ending up in places where safety can never be left to chance. What started as a few sheets of ordinary-looking glass and a handful of polymer film transforms through heat, pressure, and incredible engineering precision into a barrier capable of stopping one of the most destructive forces humans have ever created. It's a quiet reminder that some of the most powerful protection in our world isn't built with brute strength. It's built with layers, patience, and science. If you enjoyed going behind the scenes of this incredible manufacturing process, make sure to like this video. Drop a comment letting us know what factory tour you want to see next, and subscribe for more fascinating journeys into the hidden world of industrial engineering.